On Friday, we defined a new term called the electric potential energy. And once again, we drew the analogy between electricity and gravity. We said gravitational potential energy. We defined it in Physics 20 as the energy stored in an object due to its height. But really, the definition should have been the energy stored in a system of two masses a certain distance apart. We just simplified it a little bit in Physics 20 because it worked for us. The masses of the Earth, let's say, and the board marker, or the Earth and you, or the Earth and whatever it is above the surface of the Earth that has the potential energy, were so different that it worked just to say it was the energy of the board marker or of you or of whatever it is that's above the surface of the Earth. But strictly speaking, the gravitational potential energy was the energy stored in the system, of two charges a certain distance apart. Electric potential energy is the energy stored in a system of two charges a certain distance apart. So here's a charge, okay, maybe it's positive, maybe it's negative. Here's another charge, maybe it's positive, maybe it's negative. There's a certain amount of potential energy that's stored in this system a certain distance when these two charges are a certain distance apart. Now, we also talked about the change in electric potential energy, not just electric potential energy, but the change in electric potential energy. And you remember from Friday that the change in electric potential energy is equal to work, just like the change in gravitational potential energy was equal to work done as well. Okay, that was important in answering the question that we did as an example on Friday, which was probably, if you remember this little concept, the easiest question that you'll ever see in Physics 30. If you don't remember the concept, probably the most bothersome question you'll see in Physics 30, because you'll look at it and you won't have any idea what to do with it, but yet you realize, okay, or somebody tells you that the answer is simply the data that's given to you in the question. If you're given the work done and you're looking for the change, the gain, the loss in potential energy, same number. All right, we said on Friday as well that we're not likely to get a question that's just that on a unit test or on an exam. What's likely to happen is that this, as important as it is, and as simple as it is, as straightforward as it is, when it appears, it's likely to appear as part of a bigger question. So you're likely to get a bigger question that asks you something, 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 but needs you to know that in order to answer the something, 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 something. All right? Today we're going to go a little bit further and talk about a new term called electric potential. Not potential energy, but potential. Okay, there is a small difference between electric potential and electric potential energy. A lot of times we get them mixed up because we hear the terms electric potential energy. Hey, they sound a lot the same, right? But they're not the same. Electric potential energy is the energy stored in the system of two charges a certain distance apart, but potential is the amount of potential energy per unit charge. It's kind of like saying, if money is analogous to energy, okay, let's say that for a second money is analogous to energy. Let's say that there's 25 of us in this class, and let's say that we have a total amount of money in this class of $100. That would be analogous to the electric potential energy. The potential would be $4. $4 per person is analogous to potential. So potential energy is 100 because that's the total that we all have combined. Potential would be 4 because if you take 100 and divide it by the amount of people in the room, 25, we'd end up having $4 per person. Okay, we're not talking about money though, we're talking about energy. So potential is going to be not money per person, but energy per charge, energy per coulomb of charge. The symbol for electric potential is V, a capital V, okay, lowercase v would be speed. It's a capital V, and that's a little bit confusing simply because the units for potential, we look at it, joules per coulomb, but the units for potential can also be volts. So potential, the symbol V, units, volts, the symbol V. That's the only unit that we have, or that's the only quantity that we have the same symbol for the units as we do for the actual variable symbol. Right, Danica? So use joules per coulomb, use volts, whatever. $100 total, $4 per person. If you have 10 joules total, then you have maybe 2.5 joules per coulomb. Okay, potential is the energy per coulomb of charge. And that's related to something that we talked about with parallel plates, right? Potential difference. We'll define that in just a second here, okay? Good. All right, let's talk about that potential difference now. When you get a charge that's moving through an electric field, it will experience a potential difference, right? There'll be a difference in energy per coulomb of charge. Let's think about why that's the case. Okay, if a mass moves through a gravitational field, it will experience a change in gravitational energy, gravitational potential energy. If a charge moves through an electric field, it will experience a change in electric potential energy. If there's a change in electric potential energy, then there's got to be a change in potential. If there's a change in the total amount of energy of all of us, then there's got to be a change in each one of our energies. It's kind of like saying, look, we have 100. Just stop writing just for a second here, guys, okay? We have $100 total. We have $100 and we have 25 people. The total energy is analogous to total money, right? But analogous to energy is $100. The energy per person, or the potential, sorry, that should have been 25, would have been $4, right? Energy is $100. The potential would be $4 because it's the energy per person. Now, what if we went to 7-Eleven and bought a Slurpee? And the Slurpee cost $2.50. Well, the potential difference would be $2.50, right? Because that's, if we all bought one, that is, because that's the difference in energy per person. Okay, we all have $2.50 less than what we had before. We had $4 each, potential of $4. Now we have $1.50 each, a potential of $1.50. The potential difference would be the difference in potential between before and after. In other words, it's the change in electric potential energy per person or per coulomb of charge. Okay, when you move through when a charge, that is, moves through an electric field, okay, will experience a change in electric potential energy, therefore change in electric potential, and we call that the potential difference. And we can find that in one of two ways. We can subtract the final minus the initial potential. I go to 7-Eleven, my potential was $4, now it's $1.50. 150 minus $4 is negative 250. That's my potential difference, simply by subtracting the final minus the initial potential. But the other way that we can find it is to say it's equal to the change in energy total per coulomb of charge. So it's like, you go to 7-Eleven, we all spend $2.50. Okay, we all spend $2.50. That's 25 of us spending $2.50. Okay, we've just spent $62.50 on Slurpees. The change in energy was $37.50, right? Change in energy was $37.50. No, the change in energy was $62.50, right? Right. If we spent $62.50 combined on Slurpees, the change in energy was $62.50. We divide that by the number of people, which is 25, and we get a potential difference of $2.50. So we can find it by saying, look, the final potential minus the initial potential, or we can do it by saying the final potential energy minus the initial potential energy divided by the charge. We get the same answer both ways. Finally, one more term. It doesn't really go with the equations here, but is a unit that we're going to have to use from today on through the rest of the year. It's called an electron volt. An electron volt is a unit. It's a unit of energy. Just like a joule is a unit of energy, just like a kilowatt hour is a unit of energy, right? We see kilowatt hour on our power bills. Yeah, that's a unit of electric energy. An electron volt is also a unit of energy. Why do we create another unit now for energy? Why do we need another unit? We've got joules, that works just fine. Well, for the same reasons we have different units for every other quantity that we ever measure, like speed. Okay, sometimes it's convenient to measure speed in kilometers per hour. Sometimes it's convenient to measure it in kilometers per second if you're talking about an asteroid hurtling through space. Sometimes it's convenient to measure distance in meters. Sometimes it's convenient to measure it in millimeters. Sometimes it's convenient to measure it in light years. Okay, it's sometimes convenient to measure energy in kilowatt hours. Sometimes it's convenient to measure it in joules. Sometimes it's convenient to measure it in electron volts. We define an electron volt as the energy that is gained or lost by an electron when it moves through a potential difference of 1 volt. And 1 electron volt ends up being equal to 1.6 times 10 to the minus 19 joules. It's not a coincidence that that's the same as the charge of an electron. But remember, we're not dealing with charge here. Okay, this is energy. Okay, the energy, 1 electron volt, is the same number as a charge of an electron, but it's measured in joules. So how do you convert? How do you convert? Well, if you're ever having trouble, you're ever kind of stuck converting to units, as long as you have a conversion factor, there's a nice, easy way to do a conversion. Let's say we have 6 electron volts, and we want to find out how many joules that is. Let's do this. Let's say 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. And if you don't remember that, just check your data sheet because it tells you. Equals 6 electron volts over x joules. And you just solve for x. If you have the number of joules and you're looking for the number of electron volts, then just leave the one on the top blank and solve for whatever it is that you're looking for. Cross multiply. Let's have a look at example 11.8 on page 566. Having trouble even saying that page number, let alone doing the question. It says a small charge of 3.2 times 10 to the minus 19 coulombs is moved between 2 parallel plates from a position where the electric potential is 2,000 volts to another position with an electric potential of 4,000 volts. This question should ask us A, for the potential difference, and B, for the potential energy, not potential difference, but potential energy gained. And it asked for it in joules and electron volts. All right, so let's do question number 1. We want the potential difference. Remember what potential difference is. Remember what potential is. It's the energy per charge, energy per coulomb. Potential difference is the difference in energy per coulomb. Here's what I'm going to say for potential difference. Question A, I'm going to say, look, the potential is 2,000 volts. Now it's 4,000 volts. The potential difference is simply going to be equal to VF minus VI. We're going to say 4,000 minus 2,000 gives us 2,000 volts, or 2.0 times 10 to the 3 volts. It's not 2.0 times 10 to the 3 because that's what this number is. It's 2.0 times 10 to the 3 because it's the difference between 2,000 and 4,000. Now, what's the potential energy gained? Well, we know that delta V is also equal to delta E over Q. And delta E is potential energy change, potential energy gained or lost. Maybe they could also ask me for the work done. If they're asking for the work done, it would be the same as the potential energy gained. Same answer as B would be. Delta E is equal to Q times delta V. The potential energy gained is charge times the potential difference. Charge is 3.2 times 10 to the minus 19, and the potential difference is 2,000 volts. That gives me 6.4 times 10 to the negative 16 joules. There's my answer for potential energy gained in joules. What about in electron volts? Well, let's say 1 electron volt is equal to 1.6 times 10 to the minus 19 joules equals X electron volts over 6.4 times 10 to the minus 16 joules. Solve for X, I think we end up getting 4.0 times 10 to the 3. electron volts. So what's a better unit for a question like this? I don't know. They both work fine, I guess. Okay, sometimes joules are better, sometimes electron volts are better, sometimes it doesn't really matter. In this case, they asked us for both. We did it, and we can look forward and do it next time too. All right, we'll give you just a couple questions to work on here quickly right now for the next 5 minutes, and then we're going to go and finish up our unit after that.